Alright, thanks for watching, and today we will derive the wave equation from scratch, so get ready with me for an awesome physical adventure. So, step 1. Suppose you have a string that goes up and down, and what we'll consider is a very tiny piece of the string. Maybe here, which we'll assume is straight. Kind of like this. So this string is straight. So straight honey, and in particular, this is position x, and this is maybe position x plus some small increment, which we call delta x. And the derivation of this is based on the most important physics law, which is Newton's second law. Now, F equals ma. So may the force be mass times acceleration. And in order to derive the wave equation, we just need to study those three terms separately: the acceleration, the mass, and the force. So let's start with the acceleration. So study of A. Okay. And the first assumption that we'll make, so by the way, this derivation is based on assumptions which make the PDE more manageable while also being physically realistic. So here what we'll assume is that the points on the string, they only move up and down. So points on the string move vertically. So first assumption of 5. Points on the string move vertically. So in other words, there is no horizontal component of the position. So what is the position vector in this case? Well, the horizontal component is 0, but the vertical component is the height of the wave, which we define to be u of xt. So u of xt is the height of whatever wave we study. So this allows us to get s of xt. So in this case, s of xt, again, is 0 because there's no horizontal displacement, and u of xt. And in particular, what is the acceleration? The acceleration is just the second derivative of s with respect to t. So d over d squared over dt squared of s of xt. And then just differentiating both components, we get 0 and then utt x. So we are done with the a part of f equals ma. And so the next part is studying m. So f is ma, and now let's study m. So that's step 2. Study of m. And we are doing this by using density. So once again, this is our string. Maybe this is delta x, and this is delta u. So the x displacement and the height displacement. And our second assumption that we'll make is we will assume that the string has constant density, which we'll call rho. In other words, this string isn't heavier at one point compared to the other one. Assumption 2. So this string has constant density. Density rho. And to figure out the mass, we just want to use a formula of the density. So the one you might be familiar with is density is mass over volume. But that is for 3D solid. So here the analog of volume is length. And so in particular, m, which is the mass, now just becomes density times length. But once again, the density is rho. And to find the length, you just apply the Pythagorean theorem. So square root of delta x squared plus delta u squared. Delta x squared plus delta u squared. Very good. So we're done with the mass part. And last but not least, all that this boils down to is studying the force. So step 3. Study of F. And what we'll assume is that the only force on the string is the tension. In other words, the way you pull it to the left and to the right. So I think that's assumption 3. The only force on the string is the tension. Here is what I need. So once again, you have the string. This is once again an x, and this is an x plus delta x. Maybe at the fixed time t. So the only forces here are one, pulling it to the left. So that's the tension at x. And the one pulling it to the right, and that's the tension at x plus delta x. And so let's kind of study both of them at the same time. So now study of tension. So in particular, again, suppose we are at x. Then there is the force pulling it here. And in particular, the magnitude of the tension, we call this T of xt. And the angle, we call it theta of xt. So let, first of all, T of xt be the magnitude of tension. And theta xt be the angle. Be the angle of the tension vector. And then you may notice a polar coordinate situation going on. So let me rewrite this just a little bit. So once again, we have our triangle here. This is theta xt. This is T of xt. And we have the tension itself going this way. And well, once again, we do have a right triangle here. So using polar coordinates, this side is t cosine of theta. And this is t sine of theta. And in particular, what is the tension? It has components t cosine, t sine, but in the other direction. So we have this minus sign coming up as well. So tension at x, all this is, again, minus because of the other direction, and then t cosine of theta, t sine of theta, and then xt, which all this is just another way of writing minus t of xt cosine of theta xt, and then t of xt sine of theta xt. And that's it. That's very good. So that is the tension at x. And to figure out the force, you just add the tension at x and also the tension at x plus delta x. So let me do this on a new whiteboard. So once again, we have our string. So this is at x, so left point and then right point. So we have those two tensions here and here. So the force, that is the tension at x plus the tension with one, doesn't matter. So the tension x plus delta x plus the tension at x, and then what this becomes is t cosine of theta, t sine of theta at x plus delta x, and then comma t if you want, and then minus t cosine of theta, t sine of theta at xt. And that's very good. So we found the force, we found the mass, we found the acceleration. So all we need to do is put everything together. So step 4. So now we know that F equals ma. Now remember, F was the tension. So in other words, T cosine of theta at x plus delta xt minus t cosine of theta at xt, and then the same thing with sine, so t sine of theta of x plus delta xt minus t sine of theta of xt, so that is F. And now it's mass times acceleration. So remember, the first component of acceleration was 0. So if you multiply mass by it, you get 0. And then for the second component, the mass was this rho square root of delta x squared plus delta u squared, and then times utt. So it really just boils down to comparing those two components, but what we'll do mainly is just comparing the second component. Because at this point, I do want to tell you a little assumption about t. So assumption 5. So we will assume that the magnitude is constant. So we call it just capital T. So this capital T, you can treat it as a constant. And the reason I'm mentioning this is the same thing is valid if T is only a function of x. Because it turns out if you compare the first component, you will see t doesn't depend on x at all. But we still need to assume that it doesn't depend on t either. So for our purposes, we assume it's constant. Okay, now let's compare the second component and see what we get. So now step 5. So what we now have is t sine of theta of x plus delta x t minus t sine of theta of xt is ma, so rho square root of delta x squared plus delta u squared and then utt. Notice this looks a little bit like a derivative, And in order to make it a derivative, we just divide by delta x. And now, let's see what happens. So let's first calculate the right and calculate the left, see what's going on. So the right, well, notice it's rho utt times that square root term. So delta x squared plus delta u squared over delta x. But again, delta x is square root of delta x squared. So this is the same thing as rho utt square root of delta x squared plus delta u squared over delta x squared, which now you can simplify to become rho utt square root of 1 plus delta u over delta x squared. And now we are ready for our last assumption. So in this case, we will assume that this is small. So assumption 5. So this is what's called the relative displacement. So the way the string moves up versus horizontally is small. Delta u over delta x is small. And I will draw a picture of this in a second, but in particular, since this is small, it's much smaller than 1. So if delta x goes to 0, this whole thing will go to rho utt square root of 1, which is rho utt, which is one part of the wave equation. So now all we need to do is to study this term. So that was the right. Now let's study the left, which is, remember, it was t sine of theta of x plus delta x, t minus t sine of theta of xt over delta x. Remember, our assumption is that t is constant, so this is t times sine of theta x plus delta x, t minus sine of theta xt over delta x. And well, as delta x goes to 0, this just becomes a derivative of sine of theta. So t times sine of theta with respect to x. And once again, remember a crucial assumption that the relative displacement is small. So if it's this delta x and delta u, we assume this slope is small. And in particular, we have two things. So this thing, first of all, it implies that the angle is small. So theta xt is small. You can either think of it physically, well, if the slope is small, well, the angle must be small as well, or mathematically, because theta is arctangent of delta u over delta x. So if this input is small, then the output arctangent is small as well. That's one thing, and most importantly, what this implies about sine of theta, remember by trig, sine is just tangent times cosine. However, if the angle is small, then cosine is roughly 1. So here sine of theta is roughly tangent of theta, but tangent of theta is delta u over delta x. So in particular, as delta x goes to 0, this goes to ux. And that's very crucial here, because now, as delta x goes to 0, this just becomes t uxx, and that becomes t uxx, which is precisely the second part of the wave equation. And now all we need to do is to combine both parts as a grand finale. So step 6. Grand finale. Woohoo! So remember, left was equal to right, but left was t uxx, and that became rho utt. So left equals right. But then now solving for utt, we get utt is t over rho uxx. But if you let c be square root of t over rho, you then in the end up getting utt is c squared uxx. Which, ta-da, is the wave equation. And the cool thing is, this also gives you an interpretation of c, because if the tension is bigger, that speed gets bigger, and if the density is bigger, then the speed is a bit smaller. Like, think of very heavy wave. All right, now we can finally use the wave equation in the next videos. We'll try to solve them and interpret them. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.